Have you ever wondered how clouds are made? Did you know every single raindrop, every snowflake, and every hailstone each has something in common inside them that allowed them to form in the first place? Welcome to Science with Bobert. Dr. Smith and I are going to help you understand how today's scientists believe they understand how clouds form, and also how precipitation like rain and snow is created in our clouds. Now, in order to do this, we will need to see how scientists think about heat, which scientists like to call thermal energy, in order to understand the differences between solids, liquids, and gases. Scientists also call gases vapors. When it comes to cloud formation, scientists believe what happens in the clouds is literally super cool. And Dr. Smith and I will show you how to make a super cool cloud and super cool water in your own home. We will then wrap up with what scientists today only somewhat recently figured out, and that's answering the question, why is ice slippery? So let's get started. Heat is a form of energy. It is also known as thermal energy. That's because when heat is absorbed by a substance, the random and chaotic motion of its molecules move faster in all directions. That is the key behind understanding how scientists view solids, liquids, and gases. So what is the difference between a solid, liquid, and a gas? The answer is the speed of the molecules. At very low temperatures, all substances form a solid. In a solid, the molecules do not have the energy to fly away from each other. They stick together strongly through different types of attractive forces between the molecules. In a solid, it is common at the molecular level to have a repeating microscopic structure made by the molecules. Scientists can identify a solid by recognizing these repeating structures. Perhaps you have heard of crystals? Every crystal is constructed of identical units of molecules at the microscopic level. In a liquid, molecules stick together, however, just not as strongly as they do in a solid. This is because there is now a higher temperature, and that means a lot more thermal motion than in a solid. So the nice organized crystalline structure we saw in the solid is replaced with a random, jumbled motion of loosely sticking together molecules. The same attractive forces are keeping liquids and solids together. It's just that in a liquid, there is a lot of thermal motion. That is how scientists think of a liquid. Notice how some molecules in a liquid are too energetic and find themselves shooting straight out of the liquid. When a molecule leaves the liquid, scientists call that evaporation. In fact, whenever liquid molecules are present, so too are gas molecules. Just can't stop evaporation. When the escaped molecule re-enters the liquid, that's called condensation. Can't stop that either. Condensation and evaporation are constantly occurring on the surface of all liquids. In a gas, also known as a vapor, each molecule has absorbed so much thermal energy that it is moving way too fast and energetically for it to stick to other molecules. Because of this, vapors can get extremely hot. They just keep moving faster and faster as heat is added. That is why you have to be really careful around steam. It can get to be nice and fresh to the touch, or extremely hot and dangerous. The only way to slow gas molecules down is to remove thermal energy. In other words, cool it down. So if we start with a solid and slowly add heat to it, the solid will turn from a solid to a liquid to a vapor. However, cloud formation is the other way around. Water vapor molecules lose thermal energy. They slow down and condense to form microscopic water droplets. Scientists who have been studying cloud formation however, have found that this is impossible. Water gas molecules never form microscopic droplets on their own. They always need something to stick onto. They won't stick to each other at first. That means inside every single microscopic water droplet in a cloud is a very small particle. Scientists call these particles hygroscopic nuclei. Now, what is even more interesting is, what do you think hygroscopic nuclei in our clouds consist of? Dirt? Dust? Smoke? Those would be good guesses, but they are all wrong. Scientists have found that the hygroscopic nuclei in Earth's clouds are most often small particles of salt. How do all these tiny particles of salt get into our atmosphere? Salt water, our oceans, covers 75% of the Earth. When the sun evaporates ocean water, the salt remains in the air and gets picked up by the wind and blown all over the Earth. So why don't raindrops taste salty? The salt concentration is so low you can hardly even measure it, much less taste it. Okay, let's see if we can make a cloud in a jar. It seems that all we need is a container, some water vapor. We'll use the hygroscopic nuclei that are naturally in the air, and then an air pump to create wind, which should cool down the water vapor to make microscopic water droplets. Okay, Dr. Smith, have at it. What we need is some air. Got it. Some water vapor. There's definitely water vapor in the air, but not a lot. And we want a nice thick cloud. So let's get more water vapor in our container by adding liquid water. Now we need a way to cool down the water vapor. So Dr. Sam is going to use an air pump to pump a high pressure of air inside the plastic bottle and release the top, and when the air blows out, that will be the wind. It should work. Let's see. Not much of a cloud. That's because the only hygroscopic nuclei is that what was naturally in the air. So let's try this again by adding a lot of hygroscopic nuclei. What Dr. Smith is using as hygroscopic nuclei isn't salt, but smoke. Wow, what a nice cloud.